Okay, I'm thinking we are ready to get started. Okay, so first of all, thank you very much for coming. I know it's right after the great party that we had yesterday, and it's extremely tough hour to be here. And I really appreciate that you came. And you came to hear about the high-performance computing. And I wanted to start with the thing that this is not a rocket science, but it's a little bit tricky. And when we talk about rocket science, let's think about how much compute we actually need to land a person on the moon. Because we answered this question in 1969, and this was more or less the control center that allowed us, the humanity, to land a first rocket on the moon. And back in 1969, this room that was in the center of attention had whopping 12 kiloflops of compute power. This means that the entire control center could do around 12,000 floating point operations, so more or less arithmetic operations per second. This may not seem enough or not seem much, but this is what we needed to operate the stuff and land the stuff on the moon. But probably the engineers that were designing the rocket were using a top-of-the-art supercomputers back in the days. And here's the CDC 6600, also from 1969. And this supercomputer, I believe the photo is actually from 1969, but this supercomputer had 3 megaflops of compute power. So if we put it on the perspective, we had flops, kiloflops with our mission control system, and we have megaflops with a supercomputer from 1969. But you may wonder, okay, this is pretty old, so what do we have now? And well, in your pockets, I actually have a really old Android phone, so that's not good for presentation. But if you think about a new iPhones, they actually came with compute that can go up to 2 teraflops. It means that in our pocket, we have stuff that's not 1,000, but 1,000,000 times faster than supercomputer that we use to model the rocket. And if you think about your MacBooks, the new ones from this year, this is 8 teraflops of compute power. Now, going further, I want to introduce you to top 500 list. Have you ever heard about it? Hands up. So for those of you who never heard about it, this is a mostly academic list where people can join and see who has the biggest, maybe fastest supercomputer, right? And if you look on the list, the current champion is El Capitan. So this is more or less the visualization how it looks. It takes entire floor in the server room. And this currently has 1.7 exaflops of compute power. So if we put it on the chart, we have, again, 1,000,000 times faster stuff than our smartphones. That's pretty intense. But when I was browsing through the top 500 list, I was also curious about one thing. So there was this time where the CDC 6600 was the size of the entire room. Now we have something that is in our pocket that's a lot faster. So when the supercomputer was actually, when our iPhone was actually the size of supercomputer. And the answer came, it's like around the year 2000. We have 2 supercomputers back in the day that actually were a little bit slower than iPhone, and then at the end of the year, a little bit faster than the iPhone. So the 2000, it took us 25 years to miniaturize stuff from being supercomputer to actually reaching our phones. And now we are using this compute power to play Candy Crush Saga, so that's interesting thing. But if you think about the year 2000, it seems so far away. But to give you some perspective, this is what was played in the cinema. So the first Gladiator movie, also the first Final Destination, and the Scary Movie. So it takes us roughly 25 years to get supercomputer in our pocket and also record a sequel to Gladiator movie. So this is the perspective of how fast the technology goes. But while browsing the top 500 list, I also noticed one thing. So there's this date, November 2008. And on 371st place, there is something. And I was pretty, well, not expecting this. There's a Polish company that actually had bought supercomputer to power their application. We are not talking about academics doing researches and so on. We are talking about Polish business who needed to buy supercomputer. Now, for those of you who don't know, this was probably a pretender to be a Polish Facebook, a little bit, but they launched in pretty similar time frame. And well, it sees from we know from the history that Facebook had better approach with microservices, it's more scalable and so on and so on. But Nasza Klasa, the Polish company, actually had some flaws in their architecture where they couldn't go with multiple servers. They actually needed a supercomputer to run the stuff on. So like they managed to be on the top 500 list in 2008. So that's a really cool and interesting part of the supercomputer story. Now, the thing is that when I founded Let's Go DevOps, what I thought was mostly, well, doing stuff in the cloud. So supercomputers were not in our reach, at least I thought it back in the days. But we wanted to hire as many top infrastructure engineers as possible and, well, move the boundary of what we know about the engineering. So like we focus on cloud optimizations and so on, but at some point, we actually found a client that asked us to help him with his supercomputer deployment in the cloud. So the story in here starts with us having a client who ran out of bigger boats, as cloud actually claims. So first of all, it's not only me working on the project, because I have an awesome team. So Michał, Marcin, Bartek, and Krzysiek were actually involved in building the stuff together with AWS and NVIDIA guys, because, well, when we came to the table, it was not ready to be shipped, and we helped the guys ship it, or they helped us, not sure what the relation is. But because I don't have much time, maybe let's go to the meat. So first of all, let's talk about the big boats that are in the cloud, because like when you join AWS, GCP, or whatever cloud you prefer, it seems that for a standard business, there is always option to go further and have a beefier hardware and just upscale in 1 click, 2 clicks, and whatever. So let's check the biggest boats. And we have 2 flavors of it. So first of those will be the U7 something. And this something actually have 32 terabytes of RAM and nearly 900 CPUs in single instance. So this is how far you can go when it comes to compute in the cloud. The sad part here is that's actually designed to run SAP. So this is something designed for running the software that powers corporations. Like, seems quite a lot of hardware for actually managing a company. But that's not the case here. The second type of hardware that we can have is hardware that is extremely related to high-performance compute and graphics card computation. And those are P5s. So the P5s that we used, those are like a year or a year and a half old. Currently, you have P5Es, P6 were announced, so there is a faster hardware. But to give you a context of the story, what we had were the biggest instances, the P5s 48 extra large, and they are maybe not that beefy when it comes to the initial scope, because we have only 2 terabytes of RAM and 200 CPUs, more or less. But what is different is that we have this part. So each of the P5 instances have actually 8 H100 graphics cards. Those were the beefiest graphics cards available on the market, and we have 8 of those. So each P5 have 640 gigabytes of graphics memory and 32 fiber-optic cards that can be added to 3.2 terabits per second network connection. It's pretty awesome. And in here we have 16 petaflops of compute. Now, the issue that we had is that the client came with the initial demand for around 40. So this means that 16 is not enough. We need to do something with it. And here came AWS with their NDA-restricted list of stuff that they will be doing. And we noticed that somewhere in there are the Ultra clusters, and we can probably contact them to try to build it together. And we did, and they told us that it's not yet ready. But what actually is a challenge here is not only having the hardware, is having the way to connect it. So there are two ways of doing arithmetic. The one that you probably know is 1 + 1 = 2. Like if you have apples, if you have two of those, you'll have 2 apples. But there is also another part of arithmetic that you probably tested out yesterday. It's 1 + 1 = bigger 1. It means if you go to the bar and you ask for double the soda, you'll not get 2 glasses of soda, you'll actually get a bigger glass of soda. And there's a huge difference when it comes to those two approaches. We are not stacking servers on top of each other, having 10 apples. We actually need to have a one bigger glass of stuff that's in the servers. So this makes it a little bit more challenging. And to tell you a little bit about the project, if you ask me any technical questions about it, I will just say it's NDA, because I'm not sure what is public, what's not. But to give you a brief introduction to the problem that we had, because it's a little bit more complex, we knew that we need to have some kind of ultra cluster, so the supercomputer, but this ultra cluster can be actually joined by a couple of organizations. So the more organizations we have, the more compute we'll have, and it needs to be structured in the way that each of them have separate billing, and we can add and remove potential participants in the project on the fly. So that's one thing. The second thing is that ultra cluster is not the only thing that will be running for this project. So we have Kubernetes that will manage ultra cluster and other stuff that's were built to operate the entire business, and all of the organizations are actually coming in with additional features that are unique for them. And in many cases, they are not deployed elsewhere. So we have this a little bit weird setup, and the ultra cluster, so the supercomputer, needs to be in the middle, accessible by all the organizations and doing a common compute, but it's accelerated with a lot of stuff that's business related from different organizations. So this is the project. And yeah, getting to the first problem, or the problem number 0, we in the very beginning had to realize the hard truth. There is no spoon, or at least there is no hardware. Like when we contacted AWS, they told us that yes, we have P5s, but they're only available in US because all the cool stuff goes to US first, and we need to have it in Europe. And we pulled some strings, and we actually got this cute shipping tracking from AWS Cloud saying that our hardware was added to the container, transported to Europe, was on the ramp in the server room, was installed, and then we got a contact to the guy that actually put all the cables inside. So like for the 6 months of the duration of this project, we actually had a contact to an engineer on site in the AWS, because a lot of the stuff that I will show you today, it will look super easy, because it's a cool skid guide, so it needs to be easy. But like for those 6 months, we were building the stuff with AWS, so a lot of things that you now have in the UI were not there. So we actually had a technician doing changes to the physical architecture of their cloud to make some stuff work and validate some of the ideas. So the first problem was not having any hardware. It can be solved pretty much in a week. So like pretty fast delivery. Amazon is great at fast delivery, so like, yeah, let's go. The second problem, or the first actual technical issue that we had, is this, the speed of light. We know it's finite, okay, it's pretty big number, and maybe the speed of light itself is not the issue here. But what is the issue is amount of hops we need to do, amount of switches that we need to pass in order to move traffic from one server to another. And you know, in the cloud environment, this may be the server room. It's from one of the movies or series about the Silicon Valley. Those are usually big buildings, couple of floors. Your hardware can actually be spread across entire data centers. So we can have one server over here, one over there, and another over here. It will be a lot of switches to actually move around, and each of them adds additional latency to the network traffic that we have. And to give you some perspective about this relatively small supercomputer, because it's only 3 nodes, like the El Capitan has probably 2,000 of them. We have only 3. But for those 3, if you think about 1 second delay in computation, it's equivalent of more or less 1.5 hours freeze of your new MacBook, like no computation whatsoever for 1.5 hours. Now, if you are a pro gamer, you know a lot about checking the ping and how fast we can go. And in here, 1 millisecond can probably make a difference. Usually, if you have 4, 10, 12, 20, it's not a big deal. But in here, the amount of traffic that we are pushing means that if we allow for just 1 millisecond delay added on top of what we have, it's around 8 hours delay on your MacBook, right? So this is, if you look on the numbers, even the cluster is small, the amount of stuff that's going on, those 1 millisecond delays can actually add up to really huge loss when it comes to compute power. So what we did with AWS, or there is this feature in AWS that allow you to specify so-called placement group, and you have 3 options for it. You can go cluster, partition, or spread. And what does it mean? So because you don't control exactly when AWS places your machine, you can say that, okay, I'll put those in the placement group. So this means that if I pick the cluster option, I have a couple of floors, server racks, whatever. And what AWS will try to do is it will collocate all the hardware as close as possible. So this is the option that we picked, right? Everything in single place, possibly single rack, and possible single switch, so we don't have any delay on the network. The second option that you can choose are partitions. So if you have, for example, Kafka appliance, you can say that, okay, I want the groups of servers to be close together, but then the groups themselves need to be on separate hardware, because you don't want to be deployed on this VM that has 900 CPUs and have 901 CPU instances on single physical equipment, right? Because this will mean that you'll lose everything. So you can go with a partition, or you can even go with spread. This means that each of your VMs will be actually deployed on separate server, physical server in AWS. So this is a really cool feature of AWS. And we went with the cluster option because we need to be as close as possible. Now we have a second issue or second challenge to solve. And yeah, this will be this. Like what you can see here are pipes, small pipes. 32 of those pipes, like 32 network connections. It's okay if you want to pour water through those pipes because, well, you will utilize 32 of those. But if you have something bigger to push through, you need to probably cut the initial part or do something with the pipes itself. So we needed to use this mathematics of 1 + 1 = something bigger. And we did it by, well, really old technology called network trunking. And the concept is that we will use operating system and all the network equipment that will think that our couple of connections that we have, or to show you how 32 connections actually look like. So this is how many fiber optics cards we had connected between servers. They will take it all, and on the system level, they will make it a bigger pipe. So from our perspective, it's nearly as fast as a single super fast cable connection. And to get it done in cloud, it's not that easy, but there is something that's called elastic fiber adapter, and you cannot see the letters here. I don't want you to read the documentation, but there are a lot of really cool things like EFA, high-performance computing, message passing interface, machine learning, NVIDIA NCCL, and so on and so on. Like every buzzword that you can find in high-performance computing can be solved by EFA. That's my take on it. And yeah, this is what we did. So installing the driver for EFA will actually remove from the operating system those 32 cards that you saw previously and change it into a single interface that for us has theoretical 3.2 terabits per second. We were actually able in the test environment to get it up to 3.8 terabits per second. So like even better than the documentation says. So really cool stuff. And now part 3, it's not an issue, it's now a little bit of the challenge, so something that we need to have configured there, and this is called RDMA. So NVIDIA came with this idea that well, back in the days it was SLI for connecting a couple of graphics cards. Now, because we have more large-scale appliances, it's about accessing memory of different cards and having a unified space. And what documentation says is something like this, and in here you can see that, well, We change ENA to EFA. We have some lib fabric and so on and so on and so on. It's a lot of technical stuff, and everyone who joins the company and wants to learn about NCCL, we actually have a link for documentation and 2 conference speeches to actually tell in details how the NCCL work. So I don't want to bore you with the details. The goal is that for our cluster, having 3 servers, each of them have 8 graphics cards, means that application would need to put the computation in those buckets and then do the computations on the bucket itself. That's not convenient. That's not something that will scale easily. So instead, what the RDMI allows you to is to make it look like a one huge memory space. So you can load all the data that you have and do all the computations on the data by treating it as a single memory space. So this is how we made a bigger card out of 24 smaller H100 cards. Like when you think about small one H100, like yeah, it's a pretty beefy part of hardware. So this is what we did with RDMA, and in the end, that's it. Simple, right? 15 minutes now in the UI, 6 months of work where the UI was not ready, and you can have a pretty much supercomputer deployed in the cloud. So just a couple of things that needs to be solved, and they were solved by AWS and NVIDIA, so you have this option in the cloud. But there's another part of the story, because like having a huge supercomputer to do computation on the large scale is cool, but there's also another question. It's really sad if you don't have any data on the supercluster, and I'm not sure if you ever saw this appliance. So if you have a large piece of data lying in your server room, you can actually order something that's called AWS Snowmobile, and AWS will come to you with a truck that can hold 400 petabytes of data. They will put it on the truck, they will drive to the data center and unload it into the cloud. So like, this is a really cool option if you have a huge storage. For us, unfortunately, we didn't order those because all the data was already in the cloud. But yet we had a problem that the data was lying somewhere in the cloud, and we needed to get it into this ultra cluster to do computation on the data itself. And now you have a couple of options to do it. Like, first of them is to use the local NVMe drives. Those are the fastest. We have a lot of those. The issue is that in case one of those servers dies, and we know that we'll be overheating it for a while, the data is also gone. So there are some caveats to it. Okay, we can use EBSs, but with EBSs, first of all, we need to manage the data, the backups, and so on our own. The second thing is that we'll actually eat up a little bit of our network connection, so not the best probably option. We also have S3 that says that it's infinite everything. You don't need to worry about managing any kind of stuff, but it's quite slow. And what we did is we found this in the documentation. So S3 Express one zone. So AWS created an appliance, so it's different mode of running the S3 that deploys it in only a single zone, and it can be extremely fast. So like we pick the Express one zone. If you do some magic on the system level, you can actually get it to really good speed. So we are preloading the data to the cluster from the S3. That's exposed by the Express one zone, so we have a really good traffic when it comes to downloading the data for the cluster. And we only use it every once in a while. We'll need to refresh the machines, reinstall the stuff or something like this. So this is how we use the S3s. However, I wanted to end this part with this mem. Like, there is no cloud. It's just someone else's computer. And this is what we learned when we started using the S3. If you go to the documentation says no limit, unlimited storage, unlimited bandwidth, and so on and so on. But we learned that there needs to be a hardware that actually runs the software. So they are using equivalent of something large machines. That means they have 10 gigabit connection from those S3s, and like we have 3.2 terabit that we can utilize. So we will saturating the S3 connection for our buckets. And to overcome it, there are 2 things. So first of all, changing the language that we used for writing the software for pulling the data. It seems that not all the languages are equal in AWS. So some of those actually don't use features that are more or less experimental. So changing the language, like if you are doing something that's high performance in the cloud, contact the AWS guys and ask if the language that you are using, if the SDK is actually up for the challenge, because we learned that not everything is up for a challenge. And then we learned how to structure the data and how to cluster it in order to not have a single instance for the entire bucket, but we can actually shard it and launch in AWS probably 8,000 instances that will be feeding the data for us. So this is how it can be done, and that's the way to go. So I think that's all for my short presentation, only 30 minutes. But before I let you go, I have one more thing to ask you. So we did this cool graphics with the Gopher, and my marketing team actually asked me, when I showed that we do not have a call for any call to action on it, they asked me, dude, what the fuck? And I have this banner over there. I wanted it to be here. And I want you to go on our landing page, because there is no call to action, but I want you to see the cool Gopher. If you fill out the form, I will give you a T-shirt. So there are a couple of those Gopher-like T-shirts. Now, what I'm asking you in the question, in the form, are two things. First of all, think about the worst thing that you have in your backlog, something that you don't like to do, and give it as a response. You don't have to put your name and email, like just go with the meat. The goal for it is for us to be inspired, like we are tackling the stuff that you usually don't want to do and trying to solve it a little bit differently or make it a cool project. So like this is the inspirational part. The second thing are two questions about stuff that we heard a lot in those comments, and that people don't like managing laptops and the way their laptops are managed. So usually if you go to a new company, the IT division is coming to you and make sure that the laptop is connected to the office printers. There are two problems with it for us engineers. First of all, we don't want to go to the office. And the second one is we use this printer only to print out the resignation form. So like it doesn't seem to be a top priority for engineers. But what we want to do, and change it a little bit, is to deploy your laptops as a secure premise. So you will get all the tooling, VPNs, and so on, that will allow you to connect to your production environment safely and make you more productive, because we believe this is the way to go, not necessarily connecting those printers. And yeah, that's it from my side. So if you have any questions, we still have 2.5 minutes. So if not, I will be here for a couple more minutes so you can come in. I will give you the T-shirt if you fill the form. And yeah, that's it from my side. So thank you very much.